impressive biography. Well, Jochen studied not very far away from here in Karlsruhe. And then he went to Imperial College doing his PhD. And then he did a couple of postdocs in America until he returned to England when he was at UCL in Cambridge, and now in Germany he obtained a professorship in Munich. Let me say a few words about Jochen's specialities. Well, he's involved in Planck and the dark energy survey as well. And his specialities are cluster cosmology, tests of gravity on large scales, and I guess this is what we will talk about today.
That's right.
Thanks a lot.
Thanks a lot, Jochen. So it's always... Thanks a lot. So thank you very much for the kind invitation. It's always a great pleasure to come to Heidelberg. I even did this back when I was an undergraduate student in Karlsruhe, which was, I'm not sure if it changed now, but it used to be a technical university, so it wasn't as flamboyant as Heidelberg University. So we always came here, we even went to lectures to have scientific reasons to come here. And then I used to go to a restaurant down here, and it was called Maria's, and there were only physicists and homeless people. It was quite interesting because you couldn't so distinguish the people so much from the way they dress, but it was very interesting conversations I had here. And over the years, I realized it's closed now, gentrification. So anyway, I'm always happy to come back here. So today I will give you to some extent a review, but also some new work about what I pursued probably over the last 50 years. Is doing cosmology with clusters of galaxies. And yeah, I'll tell you. So I want to first introduce to you in a more educational fashion how you can use clusters of galaxies to probe cosmology. And what you will see during the talk, they are very simplifying assumptions, some of them more simpler than others, and that will haunt you the more you get towards precision cosmology, because you have to understand things a bit better. So I want to start with this very simple one-dimensional picture. What I want to depict here, so here's the density, and here's position, and we have density fluctuation, and the simple picture is if the density, the linear density fluctuation in the universe of the matter exceeds a certain threshold, this area will collapse and form a halo and later galaxy cluster. And in order to cosmology these galaxy clusters, we need to understand this process to some extent, and also we need to model it in the sense that we need to model what's called the mass function. It's the density of these objects at a given mass and a given redshift. So one thing you can see already from or can imagine from this picture, that this distribution of clusters in redshift and mass depends quite sensitively, for example, on the amplitude of these fluctuations, but also, for example, which is very intuitive, on the matter contents of the universe. The more matter there is, the different this clustering will occur. And of course, as I will show along the way, this will also depend on other cosmological quantities. So this is simple picture. You can actually get quite far, and maybe I can do some advertisement now. I saw Matthias is writing a book, and I was looking through the draft of this book on cosmology and found exactly this section here, but I didn't copy it from there. So with very simple assumptions, you can already get a very far way. You didn't tell me this. And it didn't say top secret over the draft. Okay. Oh, I'm sorry. No. Okay, anyway, so you can do very simple assumptions. You assume these fluctuations are distributed in terms of the density fluctuation in Gaussian matter. And when you do this assumption, you can calculate the probability that a region will form a certain overdensity which is larger than some critical threshold. So you can work out this probability. And in that way you get quite far, but you realize, because in the end of the day you want all mass in the universe in collapsed objects, and how this was done historically, you had to multiply this result by a factor of 2, otherwise you didn't get the normalization right. And this was done in the early 70s by William Press and Paul Schechter, and it gave the Press-Schechter mass function. Now, how to do this properly, you will also learn in Matthias' class, is basically you can use, you get clusters inside clusters, or halos inside halos. So this is the cloud-in-cloud problem, so you have to do the accounting very careful, and you can address this, for instance, by so-called excursion set formulas, and then you don't have to fudge this factor 2 in. So once you have that, the only missing ingredient, if you want, is what is actually this critical density threshold above which a cluster of or a halo will form. And again, you can, for starters, do a very simple assumption. You assume you have a spherical overdense region in the universe, and you can study this like it's a universe by itself, which is overdense, and calculate the dynamics. You can solve for the dynamics analytically, and then you linearize this dynamics, and you find above which overdensity this region will collapse, and you find this typical number 1.686. And this is, you can actually calculate forward, just as a reminder, to a nonlinear overdensity in a matter-dominated universe, and this is, in this way you get a nonlinear overdensity of 178. And this is why a lot of people speak loosely about N200 when they define masses of halos. 200 is roughly the same as 178. This process can be calculated for all kinds of cosmologies, and you find this number is actually mildly cosmology dependent. Again, you can imagine this depends on the mass. Okay, now we have this threshold, and then you can calculate analytically mass function, the density of halos for a given mass and a given redshift. And as you can imagine, then you can extend this to non-spherical ellipsoidal collapse, you get corrections, and you get a better mass function. But this is not the modern way you would go about this. The modern way is you would just do an n-body simulation. So you stick in dark matter particles, for starters, in a simulation box. You basically let Newton's law act. This is where's for this ring, because you will lynch me if I say this so simple. It's not here, but and basically you let it go, and you see typically structures like this. And then you can use that and identify overdense halos and just count them in mass bins and redshift bins. And this is sort of a typical mass function you get. Here's a logarithm of the density per unit mass. Here's the mass of the halo in a unit of 10 to the 14 solar masses, and here's the redshift. And you see what you, when you look at the shape of the surface, what you would expect. You get more low mass clusters, and you get more clusters at lower redshifts because they have more time to evolve. And this is what we will use in the cosmology analysis. We will use a mass function which comes from simulations. Right, so let me show one of the results which is at the current state most widely used in cosmology analysis. This was done in a simulation by Tinker and collaborators in 2008. So what's plotted here, I say something about this function, but for you here roughly, this is a measure of the number density of halos, and here's a measure of mass. And the question you might ask yourself, how universal is actually this mass function? You know, if I now produce a fit to these simulated points, fit change if I go, for instance, to a different cosmology. If that is the case, I cannot later then fit for cosmology if I ignore this fact. Okay, so that's why these parameters have been used here. As I say, I will define them in a second. And you find all kinds of different cosmologies can be fit in this way. There's a more modern version of this. I mean, this field is developing on a yearly basis. So this is one of the latest analyses by Despali et al. So they looked at the universality of this mass function, and they find, first when you search in your simulations for a halo, you have to define what is actually a halo. And they find if they use the virial mass, it's basically a mass associated when the potential energy is related to the kinetic energy in the cluster, the result is the most universal. And here you see this quantity mu, and that is crucial that you express everything in terms of this what's called the multiplicity. So here again you see this critical threshold above which a halo, if a linear density goes above this density, it will collapse. And here is the fluctuation amplitude, if you want, given for particular mass. So I'm trying to show this here because this becomes later important later. So here is again the the distribution of halos for a given mass and given redshift. And there are various quantities in here, and I go through it step by step. So the first thing here, this is the density of the universe, the average density. And you see, of course, this depends on it, as it should. Here, you see this sigma, which is defined here. So let me say briefly something about this. This quantity measures how mass fluctuations in the universe are correlated on a given scale. So here you see the scale dependent is k. This picks out a certain size, which is called a window function. So you get the mass fluctuation on a certain size here, and then with assuming spherical symmetry, you can convert the size to a mass. So we get the mass fluctuation on a certain mass, and you see here you have a power law dependence on this fluctuation. So that makes this quantity extremely sensitive to the fluctuation amplitude. And then finally, you have this quantity here, which brings you to from the fluctuation amplitude at redshift 0 to a higher redshift. And again, that goes in there in a similar way, so you can measure how structures grow in the universe because of this extreme power law sensitivity. So I want to show you how this behaves in a second, but before I do this, I want to tell you how to relate this to an observable quantity in a very simple fashion. So what you see here is the number of clusters in a given redshift bin and a given mass bin. So the first quantity you have to consider here is the sky coverage, how much of the sky am I observing. Then you integrate over a redshift bin, and that is multiplied by the volume element. And that is already my first cosmology-dependent quantity, because the geometry of the universe, of course, depends on what cosmological models I assume. And then you have here a mass bin, and that is what probably I will spend most of the rest of the talk about, because that you have to relate to what you actually observe, because we are not observing mass directly. And the cosmology dependence is driven by this volume element and the mass function I just showed you. And I want to show you how with this slide. So I assume here a certain cosmology which has omega matter 0.3, the matter contents, the fluctuation amplitude, Hubble parameter, it has a cosmological constant, some sky coverage doesn't matter, and some limiting mass. So I'm integrating all masses to infinity. And this is what I get for this cosmology. So here is the growth factor of structures. It is normalized to be 1 today, so you see how structures grow over time. And here is the volume element for this particular cosmology. And now I want to show you, if I increase the mass contents, from 0.3 to 0.4. Now, first of all, sorry, I forgot this is coming up. So this is the number count you predict for such a cosmology. Okay, whatever. I will compare the shapes later, then this becomes more meaningful. So you see, you have sort of a sweet spot at redshift a half, where for this kind of setup you find most of the clusters. Okay, so now let's see what happens if I change to a higher mass contents. So first, you see here, the structures are growing faster over time, but the volume element becomes a bit lower for this cosmology. Okay, and now let's see what this means for the cluster counts. So here's our original cosmology, and you see you find many more clusters, as you would expect if you have more matter available. You can sort of roughly depict what the signal to noise would be in such a setup. So what I'm assuming here is just in a particular redshift in there's Poisson noise, and you can look at the difference between this and you see this is quite significant. So this is what we will exploit later to do cosmology. So now let's go to the fluctuation amplitude here and see what changes. And here we see, so we go from 0.78 to 0.85, you see a huge increase in the number of clusters, and this is a very strong signal. The remaining thing I want to discuss is these W factors here. So that was sort of one of the, I wouldn't call it holy grail, this is too strong, but understanding the nature of dark energy, you want to understand how is the pressure in the dark energy component related to the energy density. Just for the non-experts, this W is -1 for a cosmological constant, but there is no reason a priori why it shouldn't be different, so we can study how this would show up here. So again, here I go from -1 to -0.8, and you see quite some difference in the growth factor, a little bit of difference, or more difference in the volume, and this gives you the different number counts, so you see this is already potentially much more difficult to measure. You see here this interesting structure appearing in the signal to noise, and I will say something to this in a second. You can also look when you go even low, when you go higher in this W, you find this plot, and here is some time-dependent W, which has also been discussed. So you see this typical signature here, and basically the low redshift part is driven by the change in the volume factor, while the high redshift part is driven by the change in the growth of structures in the universe. Right. So now I want to come closer to observations. So there are a few different ways you can observe clusters of galaxies. So one is you use the X-ray signature of the intercluster gas. I'm not going to talk about this in this talk. You can use the Sunyaev-Selkovich decrement. I'll explain in a second what that is. In the effective temperature of the cosmic microwave background photon. So this is depicted here. You can use weak and strong lensing. Matteo Maturi talked a bit about this today. And then so I will not talk about this, and then you can just look at the most historical method, I guess. You just count galaxies and see if they're over dense regions, so optical methods of galaxies. Right. Now before I do this, so what I showed you here, this is bad going back, you need sort of some mass in here, but you will not observe mass directly in these observations. You will have either some temperature fluctuations, for example, for the Sunyaev-Selkovich effect, you will have X-ray luminosity, or you will have just number of galaxy members. And they have to, in order to do this, to be related to the mass of the galaxy clusters, in order to exploit this. So when I go forward here, so in order to do this in a proper fashion, you need to assign a likelihood for, I call this here observed mass, but this could be any observable given a true mass. And if you're going to model this, of course, you can be guided by the physics involved, and I will show you later how this works, for instance, for the Sunyaev-Selvovich effect, when you look for the pressure in the intracluster gas. But if you have, for instance, look at the number of galaxies, the richness of the clusters, there is not really a deep guiding principle, apart from, well, the cluster will be more massive the more galaxies you observe. So you need to model that in some way with the given uncertainties. Okay? So here's, for instance, a very simplistic scaling relation where you just assume a power law between the observable and the mass. And also in this distribution you can allow for a scatter in this relation, or you have to allow for a scatter in this relation, and that quantity is actually even less clear what you assume for the parametrizations there. So, and if you do this, then you have to fold in this likelihood between the observable and the mass in your procedure to calculate the predicted number counts in a certain thing. So here's an example of this parameterization, what could happen. So again, I write down here the number counts, and I assume that I have a log normal scatter between the observable and the mass, and when you work that out, you get a Gaussian, you get an error function. Now switch this off in this integral. And I just want to show you what happens there. So if you assume this scatter is 20, 30 or 40%, you increase the number of clusters in the sample. And that is because if you look at the shape of the mass function in terms of mass, there are so many more low mass clusters than high mass clusters, so they scatter into your sample if there's an uncertainty, than the ones you lose, because you lose less high mass clusters. So you increase the overall number of galaxy clusters. That in itself is not a problem, as if you know the scatter perfectly well. Okay? If we can predict what the probability distribution is perfectly well, we can predict this, but unfortunately we cannot. So this is from an analysis which was performed by Lima and Hu back in 2005 already. So they looked at a forecasting exercise, what is the uncertainty on this equation of state factor, given some uncertainty on the prior knowledge of the scatter, and you see if you go sort of in the 20% region here, the uncertainty goes way up. So you need to understand this quantity, I would say, better to 20% in order to do this precision cosmology. Of course, you can still fit it for the amplitude or the matter contents. So the prior under uncertainty and the scatter is absolutely essential, and I come back to this when I discuss the particular probes. So now I want to come to a topic which I worked on early on in this context, is exploiting Sunyaev-Selvovich effect for observing galaxy clusters. So I want to briefly explain in one chart what that is. So here you have the photons released from the last scattering at the cosmic microwave background, and they pass through a cluster of galaxies which has, there are free electrons in that, and you get Compton scattering there. Now this Compton scattering conserves the overall number of photons. So what happens if you observe this now? You find, of course, they gain energy in this scattering process from the hot electrons. You get a redistribution of the Planck spectrum from low frequencies to high frequencies. So if you would observe this, for instance, in a low frequency region, you would see a hole in the sky compared to your background. Okay, now interestingly, this effect is independent of redshift. So because the light is dimming by a redshift factor 1/1 plus z to the power of 4, but the density of photons is of course higher by exactly this factor at the time the scattering occurs. And that was first discovered in 1972. It's quite interesting this reminded me when Bjorn gave his talk before. about his early attempts on the ISW. When you speak to Sun Yat, he says he would never have believed one can actually observe this when he did the calculation, and because it was such a tiny effect. And then the first really unequivocal observations was done by Bergenshow in the early 80s, and now we have hundreds of these objects discovered by the Sun Yat effect. And this is actually what I want to talk about now in the context of the Planck satellite. This started, my involvement started here, April 2007. There was a new professor here, eager to work on Planck. It was you. Sorry, reminding you. And it was actually, I think, I discussed this on the balcony of this building over there. Is this possible? We had a meeting there. And so, no, that's okay. So I had a code to do cluster cosmology more forecasts, but I early on linked this to Monte Carlo Markov chains and into Fisher matrix, and that turned out to be very useful. So what I show you here is the first Planck cluster sample. So here you see the galactic cut, and these are about 190 clusters with a signal to noise of larger than 7. 188 of them had redshifts, 184 spectroscopic, and 71 can be used to understand, and I come back to that, to understand the relation of the observable in this context, the mass of the cluster. So what you see here is the redshift distribution of these clusters. And I'm not saying yet something about the light, so just look at the data points. This is what has been measured. So as I said to you before, in order to exploit this, you need to understand the relation of the mass and the observable. So we are slowly working to this. So first of all, we assumed this Tinkermann's function in that analysis. We measured, well, estimated the scaling relation between the Y decrement, this is sort of this Sunyaev-Seldovich decrement in the distribution, in the frequency distribution of the cosmic microwave background photons. And basically that quantity is related, if you calculate it, to the line of sight pressure of the electron density in your cluster, because this is how the Compton scattering operates. So when you calculate this effect, essentially you have a measurement or pressure, if you want, of the cluster. And then, of course, you need to be careful how these clusters are selected, because the way Planck operates, some points of the sky are observed more often than other points. So you're more sensitive in one area of the sky than in the other area of the sky, so you have to fold this into your analysis. And now this looks quite horrible to some extent, but as I just told you, the observable is the pressure in the cluster. And the pressure, as we know from the gas, it's related to the temperature. Roughly speaking, the temperature is related to the kinetic energy in the gas, and if the system is virialized, that's related to the potential of the cluster, and the potential is, of course, related to the mass of the cluster. And that you can all calculate analytically. However, we know already clusters don't behave completely so neatly. They are inspired, or the cluster gas, by the virial relation, but they can deviate from this. And this is sort of depicted here. So let me first come to the second relation. So here you see the mass, and here you see the quantity you measure, this decrement in the, if you want, in the CMB flux. Okay, and that depends also on cosmology. You here have here angular diameter distances because you look at angles on the sky. You have some normalization factors here, and you have some redshift dependencies here. And you're sort of what's modeled here in this beta, in this alpha, in this Y star, and YB, is that we don't know this relation exactly. In a similar way, you have to look what is the size of a cluster, and you measure that. So here we have these indices 500. What they mean is we look at a radius where the overdensity in the cluster is 500 times the average density of the universe. Okay, so here you have again the angular diameter distance, you have the mass coming in here, and you have the similar quantities as down here. This theta star is about 7 arc units. That's a constant just to get the units right. Everything else are unknown constants. However, you can use X-ray measurements to nail down some of these constants. And they are given here. So here's the logarithm of y star, the alpha, and the beta. So you see in the beta, they have quite large uncertainty because in these samples you don't have so high redshift coverage, so there's a large uncertainty on this quantity. In addition, so this is your scaling relation, you have to allow for scatter of an individual cluster of this scaling relation, and that is given here. So for these quantities, mainly X-ray observations have been used, and this is what I'm showing you here. So here you see the X-ray flux versus the true mass of the cluster, and from that you can infer an SZ flux, so the Y SZ, and then you can fit for this scaling relation and get some priors. Now the biggest headache is actually this parameter here. This is called the hydrostatic bias, and there the situation is far less clear. So you see you cannot directly measure this as a degeneracy. You can only go to simulations and see what simulators tell you. So here's a 1 minus b factor, and you see the standard assumption would be that this is 1, but the simulations are sort of starting from 0.7, maybe going to up 1.05. And that we cannot really say a priori what this number is, so we have to fit for this simultaneously in the analysis. Now this is what I said before, you know, the sky coverage, the coverage of the sky is not equal for each point of because of the scanning strategy of the Planck satellite. So you see some points which are scanned more often and some are less, and that you have to fold in because we select clusters by signal to noise. So of course the signal is stronger in some areas than in other areas. And it turns out, luckily, this can be, so this has been checked with Monte Carlo simulations of the noise map, but you can fit this fairly nicely with an error function, given on the size of the beam you want to choose. Okay, and this is here, so you have to fold this into the analysis, and when you do this, you come up with these number counts, and then you can fit your best cosmology model. And this is what's in the blue solid line here. However, Planck, of course, is not a designed machine to do so. You have cluster counts, you look at the primordial fluctuations in cosmic microwave background, and they have a much more robust way to estimate cosmological parameters. So if you use Planck itself and use a cosmology fit, you find this green line. So you see already there's something strange going on. So let me come back to this in a different way. So what I'm showing here are 3 cosmological parameters. Here is the sigma 8, which is this measure of the fluctuation amplitude. Here is the matter contents of the universe, and here is the Hubble parameter below. In order, because these quantities are quite degenerate with the Hubble parameter, you need an additional measurement of the Hubble parameter, and one way is either to use measurements of the Hubble Space Telescope or baryon acoustic oscillations, which come from the distribution of galaxies, to anchor the Hubble parameter. So and this is what you see here for these 2 types of analysis. So the first thing you would take away here, this looks fairly consistent, but if you combine this with BAO, you get actually, well, would I say significant? You get a different Hubble parameter, which is in slight tension as if you use, for example, HST for this type of analysis. Now, to see, get a feeling how robust this is, we have also done some studies where we opened up the parameter space. So the red line is the analysis I just showed you. Here you see the constraint on the fluctuation amplitude of omega matter. And the blue line is if you open up the redshift evolution of the scaling relation. So there was this parameter beta, if you remember. And so if we don't specify this, of course, we get larger contours like this. Also interesting, I told you before, we take the mass function from simulations. So you might ask yourself rightly, well, it's from a simulation, how correct is this simulation? So you compare with other simulations, and there you get quite comparable results. And then finally, if you open up this bias parameter to be between 0.7 and 1, you get this huge magenta contour here. So this analysis depends quite sensitively on what priors you assume. Right, so then in 2015 we published, well, the latest Sunyaev catalog, and that consists now of almost, well, of over 1,600 objects if you go down to a signal to noise of 4.5. Some of the data you don't know if it's contaminated, so you look at the infrared signal, so these are the red ones are taken out here, and only the green ones are retained because we had other observations which confirmed these are actual clusters. And this was an analysis which I find quite important in this big collaboration, which was performed by David Sutton, because you can't recognize in the papers. It's actual author. Right, so what I'm showing here is the mass distribution of these clusters. So what masses we get if we assume the scaling relations from the X-ray versus the redshift. So the crosses are the data we already had in the first release, and the solid points are the ones which were added in 2015. And we had various different ways to discover clusters in these maps, most of them based on a multi-frequency matched filter method, and the ones which were found in all the methods are in the circles. The different colors depict different signal-to-noise levels. Okay, now because we had so many more clusters, we could split up the sample, this is still working, not just in redshift, but also in the observables. So you have basically, you count clusters in signal-to-noise bins and in redshift bins, and of course when you do this, you have to change the modeling accordingly. Right. Now the biggest problem, again, is how to fix the scaling relation and how to fix the hydrostatic bias. And there, lensing plays a very crucial role, because lensing gives you a way to measure the mass of a dark matter halo more directly. And we could use different priors on this. So one project was weighing the giants that was using ROSAT data, X-ray data, and had a dedicated program on Subaru and CFH-TLS to follow up these clusters with weak lensing, and then you could estimate this hydrostatic bias. In a similar fashion, the Canadian Cluster Comparison Project compared X-ray data and weak lensing data, and then you can use the cosmic microwave background itself is lensed by these clusters, and you can get an estimate of this bias from there. So basically this was our baseline from the 2013 analysis, and now we could shift this to better observable quantities. So the picture here is which doesn't come out really nice, I just realized, I'm sorry, from the Weighing the Giants paper. Okay, and this is what we get here. So here, again, for plotting purposes, I just show this versus redshift. So you see these data points here. And the lines are various best fit results with assuming different priors. Here is basically the mass scaling law, and so here you bin the clusters in redshift and observable, you leave the mass scaling law is constrained by a prior or completely free. In a similar way here, just the redshift bins are used because that allowed us to compare better to the 2013 results. And when you do cosmology with this, again here's the fluctuation amplitude and the matter contents. You find the following. So here is the red contour is if we use the Neaev-Sellovich counts and the lensing power spectrum to estimate the mass. In gray underneath here is the baryon acoustic oscillations and CMB, and then there are various priors on the scaling relation coming from grains and giants. You get the green contour here from the CCCP, and here from the CMB lensing, if you open up this scaling relation and don't fix it. Okay, so you get these results from the counts. So you see, again, this depends quite sensitively what you assume on your mass-observer relation, but it's all consistent with each other. Now, for that reason why this is so uncertain, I'm not going into the game because of this discrepancy. Let's say you use this data set and this and want to get this in agreement. Well, it's only 1.5 sigma, so it's not the... You can play games and change your cosmological model, like for example, fit for a neutrino mass or so. And then this pushes this up a bit, but I don't want to go there yet, because I think, well, this is my personal belief, but I think the astrophysics of clusters might need to be understood much better before you do games like this. So I'm not showing you plots. This is sort of this plot just in one dimensions over this hydrostatic bias. So you see, if I blindly would get the SC cluster counts in agreement with the primary CMB, I get this very low number in the hydrostatic bias. And if you might remember this plot I had from the simulations, simulators don't really see that in their simulations, such a bias. So that is really hard to get. Now, and the green and red and blue contours is what you get with when you combine with different priors from mass observations from the lensing. Okay, so I think that is sort of the status here, and of course you can then think, oh, what happens if I open up the redshift evolution of this scaling relation? So this is what the black contour is what you get when you fix the redshift evolution, and this is the reddish contour is if you open up the redshift evolution and also have the power law with respect to mass relatively free. And of course then the error gets larger if you do that. Okay, so here I want to finish the set and move on to optical cluster finding, which to some extent is even more prone to the understanding of the scaling relation, but as you will see, this doesn't yet give competitive errors, and that you don't have to worry so much about precision. But we need to understand this in the future. So that's one example, that's the max BCG. I'll tell you in a second how this roughly works. And in this analysis by Köster and then the cosmology by Rozzo, about 14,000 clusters were found in the Snow Digital Sky Survey, and there was a red sequence method used, and the mass proxy is the richness, the number of galaxies you find in the cluster. So how does this maxi BCG work? Basically, you have a few assumptions. You assume there's a 1/radius decrease of the spatial clustering of galaxies in clusters in the 2D projection. The most luminous galaxies in clusters occupy the tide sequence, the red sequence, and you assume the brightest clusters galaxy resides in this ridge line. So you search well, for the most massive galaxy and start searching around that, and that's how you build up your cluster catalog. And in that way you also get simultaneously a redshift estimate from the photometry of the cluster center and a richness, how many clusters belong to that. And you find that if you have richnesses of more than 20, you have about 90% completeness. So here is the counts you get. So now I'm doing not the counts versus redshift, I'm doing them just versus observable because it's known in this analysis the redshift range is very narrow. So here you find the numbers versus the richness. Okay? And I'm not saying anything yet about the best fit models, but what you see here, if you vary cosmology, well, here quite significantly, admittedly, you get a difference. But here this plot is with the error bars, okay, so they're quite tight. Right. So now I have to model this, how this richness is related to the true mass. And again, I have to assume a scaling relation, and there is some embarrassment, because I don't know what the scaling relation is a priori. I don't have this guiding physical principle that, you know, the cluster gas is virialized. I just can say, well, I will probably have more massive clusters if I have more galaxies in the cluster. So all I do is assuming a power law here. But here I cannot use any prior, because I have no a priori knowledge. So you see here in this, what I showed you, we have now 14,000 clusters. Before, in the Planck analysis, we had about 1,600, but as you will see, the cosmology constraints are less competitive here, because I don't know how the mass is really related to the observable. In addition, you need to understand the scatter in this relation, and that has been calibrated by using this optical data, X-ray data, and weak lensing, and you find about 45% in the mass. Now the problem is, for this sample, let me see if I come to this, I come to this later, but well, I mentioned it now, there are two weak lensing analysis papers which disagree by about 5%, so we add this as an error, because we cannot judge who is right of these guys. Right. So you fold this into your analysis in a similar fashion as before, you get these error functions. And then in addition to this, you have lensing observations. So what you do is, you stack clusters of similar richness, and then do your mass estimates from the weak lensing signal in these stacked clusters, and you find mass measurements. And this is what's given here. So this is from an analysis by Johnston, and Sheldon. And basically this allows you to fit simultaneously for this scaling relation in the number of galaxies, the richness, and the mass. Now what we did in this analysis, and I haven't said anything about this yet, this is not all the information you can have on clusters, because we have so many clusters distributed on the sky. We can now also probe for the spatial clustering of clusters. Okay, and we do this in Fourier space, so we use the power spectrum of these clusters. And this has been measured by Gerd Hutzi and collaborators. So what you see here is a power spectrum, which is the Fourier transform of the correlation function. And here are various models, okay, you see on there. However, to use this, you have to include quite a lot of effects where you only have rough understanding. So first of all, because this is working in Fourier space and not in angular space, you have to include what are your errors on your photometric redshifts. You have to include the circular geometry. You also might want to include some factor which allows for non-linearities and redshift-based distortions. Okay. In order to estimate these errors, one can, for instance, use a jackknife method or Monte Carlo of about 1,000 mock observations. So if you want to exploit this shape, you first have to understand how this is related to cosmology. The first thing, you might understand the linear distribution of dark matter particles in the universe, and from there you can estimate the spatial clustering. The first thing which comes in, we look at halos, which are heavily overdense regions of the dark matter field. And what you get then is you get an enhancement of this clustering, which is called the bias. Interestingly, that you can calculate from the mass function, what that is. But you need to model other effects, and this is what Hützi suggested. Some of them are more clear, so there's some effective bias. He had some rough nonlinear modeling, and then there's some contribution to user uncertainty in the redshifts here. And what he finds in this analysis, he finds some best fit points for the power spectrum, assuming a fiducial cosmology, but we will open up this parameter space now when we fit for cosmology simultaneously. And here it's just a relation how you get the bias analytically, and we can do that. But in addition to this relation, we allow for an uncertainty in this bias because of the uncertainty in body simulations. Of course, when you combine the power spectrum of galaxy clusters with the counts, you have to be careful that you don't double count information. So you have to look at the covariance between these quantities. So we estimated this from simulations, and we found for the errors which we will encounter here, this doesn't play a role, but this is one point which is potentially important for the future. And so here is what we used. We used the flat lambda quota matter universe with some photo C error. That's quite tight because, of course, clusters contain many galaxies. And an uncertainty in the mass estimate, and then the same uncertainty on the scatter as before, and an uncertainty in the bias, and then we opened up this parametrization of the power spectrum. And this is what you get here. So here again is sigma 8 as the fluctuation amplitude versus the matter. So if you only use the counts, you get the blue contour. If you only use the power spectrum for clusters, you get the yellow contour, and if you combine, you get the green contour. So this definitely is additional information, and we were, I guess, almost the first ones who have used this, apart from Peter Schücker, who explored that in the early 2000s. And then you can combine this with the primary CND, and you get some meaningful constraints. What's also interesting, we couldn't, of course, turn around what do we learn about the scaling relation of the richness, and this is what we get here for these numbers. A little example we did here, and I'm not going much into this, you can also try and fit for primordial non-Gaussianities, and you see when you add the power spectrum, that's relatively sensitive to that, but nothing to be compared to the primary cosmological background. Okay, before I come to the end, I want to showcase some new work which we just explored. It's basically now we have sort of built up. We have counts in redshift, we have counts in the observable, we have the clustering of clusters, and the next natural step is to cross-correlate the galaxies with the clusters. So here we used the newest public catalog from RedNapper for clusters, which was done by Rykov et al., which contains about 26,000 clusters in the Sloan release 8. Which is about 14,000 square degrees, has 42 million galaxies, and gives you this redshift range, and we cut at richnesses above 20. And what we did a map-based approach, so we basically counted the density of clusters and galaxies in pixels, and then we can correlate these pixels. So this is a bit technical slide. And you get these two pictures, so here's the galaxy map, and here's the cluster map, and now you can cross-correlate this. And the way we did this, because we didn't want to use really the spatial information, we only wanted to use angles on the sky, so we calculated spherical harmonics in an L range from 20 to 500, and got this result here. So what you see here is the angular clustering. Here the galaxies, here the clusters, and here the cross-correlation between them. And one interesting thing we learned when we started first looking at this, we found the dashed lines, and I tell you what we did then and what we learned on the way. So, in order to model this, you have to model in the noise from the counts. And when you model this, you have to be a bit careful that, there's not just shot noise, there are also exclusion and nonlinear clustering effects. And essentially what we ended up, we fit for noise amplitude, because this did not work. And if you fit for the noise amplitude, you get the solid lines. So that was a big breakthrough when we did this, because that allowed us to model the noise correctly. And then we could estimate bias parameters. So you see here the galaxy correlation, which is biased compared to the underlying dark matter distribution. The clusters are more biased because they have higher masses. And we wanted to check if the cross correlation gives the arithmetic average of the bias, as you would expect from a rough analytical analysis. So if you don't model the noise correctly, this is what you get. So this is a bias on the galaxy, this is on the clusters, and this is what we measured first on the cross correlation, and this is what we would have expected. This didn't work. If you model the noise correctly, you get this relation. So this works. Okay, so this is just to showcase this work, and of course, all I have showed you sort of in the optical domain now is sort of building up to exploit this for the dark energy survey. And I just want to show you what's going on here. So this is from the science verification data, the cluster catalog, various richnesses. And here we have the richness versus the mass. And we have to model that. We have now lensing masses as well. So we can model this and calculate the covariances, and this will give us cosmological constraints, which you're not allowed to see, okay, so you haven't seen them. But they will come out early next year, and I want to advertise again Matteo Constanzi, who is doing a lot of the analysis here. So I want to summarize. So I would argue clusters of galaxies deliver interesting constraints. From SZ clusters we have attention with primary C&D constraints. I still believe the astrophysics of clusters might need to be better understood for this. The optically selected clusters are beginning to deliver constraints. The spatial distribution of clusters with complementary constraints, the cross-correlation between clusters and galaxies opens new windows. For example, you can measure the average concentration of clusters. And there are now many more to come. So the dark energy survey delivers already beautiful data. The next on the agenda is Rosita, and then Euclid, and this is just from our core proposal where Stefan Hagstotz used this machinery to predict the uncertainty on neutrino masses you could measure with such a survey. Thank you very much.
Thank you very much. Any questions, please?
The hydrostatic bias is mysterious. How is it justified? You could probably explain pressure contribution from turbulence and magnetic field, that they should be way below what bias gives you, isn't it?
You mean the value is mysterious here?
Very, very low.
Yes, I mean, so as you know, oh no, I went too far. So there's this, sorry. I wanted to show these simulations. Here. So here is the measure of the hydrostatic bias in a whole plethora of simulations. And as you see, so here's one, well, in these mass ranges, you barely get so low. I mean, this is impossible. So it's not clear what to do. So it might be a combination of both cosmology, but I don't want to go there yet. I think it's not well known enough for. Of course, you can, how shall I say, you can get rid of the problem entirely if you, I don't know, have very high, relatively high neutrino masses. I think it's premature to play with the cosmology to get rid of this problem. But maybe you're telling me I should do this.
No. I was just wondering whether there's any classification for hydrostatic bias as large as that.
Well, as you see, I don't think so. I mean, if you leave it with that, I show the plot. So here, the black. This is if you don't use any mass priors and just combine the primary C and B, as said, and leave the hydrostatic bias completely open. You're pulled by the strength of the primary C and B in this direction. But maybe that's not the right thing to play. If data sets disagree, I always have stomach aches to combine them in the first place. But I don't know any Bayesian guiding principle which tells you really not to do that. Statistic, does statistic tell you that you're allowed to combine theta sets? Not really. But I wouldn't do it. I mean, I just... But that is probably, you have to formulate this it's a prior prejudice we have. So if you formulate it in the prior, you're sort of pulled over here. You see, when you use these mass priors, maybe this one can live with this, but it's not what simulators see.
Yeah, I mean, I understand the argument that just find it difficult to understand where they should.
Unfortunately, well, if I would have an answer, I probably would have presented you that paper. is what I even said before when we used the mass estimate for the optical analysis, or after actually. You know, we used the Mandelbaum paper and the Johnson and Sheldon paper, and they disagree systematically by 5% in the mass estimate. I don't think anybody knows why. There wasn't any follow-up with them. We just opened up the error because of that, because we were not in a position to decide who is right or who is wrong. And I don't know, I mean, it's a different group of people. But it's just, I mean, here it looks like 1 sigma overlaps.
Maybe you can bring them into agreement. I was wondering about the systematic differences.
All right. Okay, thank you very much, Jochen.